Okay. The crossroads. We have come to a crossroads in our story. This is where calculus becomes modern and progresses from the mystery of course to the mysteries of motion and change. It's where calculus starts to wonder about the rhythms of the universe, its ups and downs, its ineffable patterns in time. No longer content in the static world of geometry, calculus becomes fascinated with dynamics. It asks, what are the rules of motion and change? What can we predict about the future with certainty? In the first centuries, since calculus reached in this crossroads, it has branched it has branched out from algebra and geometry to physics and astronomy, biology and medicine, engineering and technology, and every other field when where all is in flux and change never stops. Calculus has mathematics this time, and it has offered us hope that the world we live in, for all its unfairness, the misery and chaos, may be reasonable deep in its heart, where, where it follows mathematical laws. Sometimes we can find those laws through science. Sometimes we can understand them through the calculus, and sometimes we can use them to improve our lives, help our societies, and change the course of history for the better. The pivotal moment in the story of calculus occurred in the middle of the 17th century when the mysteries of course, motion, and change collided on a two-dimensional grid, the XY plane of Fermat and Descartes. Back then, Fermat and Descartes had no idea what a versatile tool they created. They intended the XY plane as a tool for pure mathematics, yet pure the start. It, it too was a crossroads of sorts, a place where equations and where equations meet curves, algebra meet geometry, and the mathematics of the East met that of the West. Then, in the next generation, Isaac Newton built on their work as well as on the work of Galileo and Kepler, and brought geometry and physics together in a great synthesis. Newton's spark, Newton's spark set off the fire that lit the Enlightenment and caused a revolution in Western science and mathematics. But to tell that story, we need to begin with the arena where it all took place. Takes a reply. Where students took today take the first course in calculus, they spend the entire year in that plane. The term of art of this subject is calculus of function and of one variable. Our discussion of it will occupy us for the next several chapters. We begin here with functions. In the centuries, since curves collided with motion and change, the XY plane has become even more vital as a cube. It's used today in every quantitative field to graph data and uncover hidden relationships. We can use it to, to visualize how one variable depends on another, how x relates to y, while everything else is held constant. Such relationships are modeled by functions on one variable. They are written symbolically as y equal fx, which is pronounced y equal f of x. F denotes a function that describes how the variable y, called the dependent variable, depends on the variable x, the independent variable, assuming everything else is nailed down and held constant. Such functions model how the world behaves as its tidies. A cause produces a predictable effect. A dose stimulates a predictable response. More formally, a function f is a rule that assigns a unique EY to each x. It's like an input-output machine. Feed it x and it spit out y, and it does so reliably and predictably. A few decades before Fermat and Descartes, Galileo understood the power of this deliberate simplification of reality. He meticulously changed just one thing at a time in his experiments while holding everything as constant. He let a ball roll down a ramp and measured how far it went in a certain amount of time. Nice and simple, distance as a function of time. Likewise, Kepler studied how long it took a planet to orbit the Sun and related that period to the planet's average distance from the Sun. One variable versus another, period versus distance. This was the way to make progress. This was the way to read the great book of nature. We've encountered examples of functions in the previous chapters. In the geometry-based example, x was the number of slices eaten and y was the number of calories consumed. The relationship in that case was y equals 200x, which produced a straight line graph in the xy plane. Another example came up when we studied how the length of the day changed with the seasons in New York City in 2018. In that setting, the variable x represented the day of the year and y was the number of minutes of daylight on that day, defined as the time from sunrise to sunset. We found that the graph in that case oscillated like a sine wave with the longest days in the summer and the shortest days and the shorter in the winter. Function of functions. Some functions are so important that they've been given their own buttons on the scientific calculator. These are mathematical celebrities like x squared and log x and 10 to the x. Admittedly, most people don't have much use for them. They are needed for making change or deciding how much to tip in everyday life. Numbers are usually enough. That's why when you press the calculator app on your phone, by default it offers you a basic calculator with a number from 0 to 9 on it, as well as the 4 basic operations of arithmetic: addition, subtraction, multiplication, and division, and the button for percentages. Those those are almost those are all most of us need as we go about our business. But for people in technical professions, numbers are just the beginning. Scientists, engineers, financial quants, and medical researchers need to work with relationships between numbers, which show how one thing affects another. To describe relationships that like to describe relationships like that, functions are indispensable. They provide the tools needed to model motion and change. Generally speaking, things can change in one of three ways. They can go up, they can go down, or they can go up and down. In other words, they can go, decay, or fluctuate. Different functions are suitable for different occasions. Since we're going to be meeting various functions in the pages ahead, it's helpful to recall some of the most useful ones. Power functions. To quantify growth in its most gradual forms, we often use power functions like x squared or x cubed, in which a variable x is raised to some power. The simplest of these, a linear function, in which they depend variable y goes in direction proportion to x. For example, if y is the number of calories consumed by eating 1, 2, or 3 slices of cinnamon raisin bread, then y grows according to the equation y equals 200x, where x is the number of slices and 200 is the number of calories per slice. However, there is no need for separate x button on the calculator. Between multiplication serves the same purpose. Here, 200 calories times the number of slices of bread equals the number of calories consumed. But for the next kind of God in the hierarchy, the type known as quadric God, it's very helpful to have an x squared button on the calculator. Quadratic growth is less intuitive than linear growth. It's not just a matter of multiplication. For example, if we change x from 1 to 2 to 3 again and ask how the corresponding values of y equals x squared change, we see they from 1 squared equals 1 to 2 squared equals 4 and 3 squared equals 9. Thus, y values got in increasing steps by delta y equals 4 minus 1 equals 3, then by delta y 9 equals 4 equals 5. If we keep going, they increase by 7, 8, 11, and so on, following the pattern of odd numbers. Thus, for quadratic growth, the amount of change itself goes up as we increase x. The growth goes faster as it proceeds. We already saw this curious odd number pattern in Galileo's inclined plane experiments, in which he timed balls as they rolled slowly down a ramp. He observed that when a ball was released from ease, it rolled faster as time passed, such that in each successive increment of time it traveled farther and farther, with the successive distances growing in the proportion to the successive odd numbers 1, 3, 5, and so on. Galileo realized what this triple rule implied. It meant that the total distance the ball rolled was proportional to time. It was proportional to time squared. So in the study of motion, the squaring function x squared arose very naturally. Exponential functions. In contrast to a math power function like x or x squared, an exponential function like 2x, 2 raised x, and 10 raised x describes a much more explosive kind of growth, a growth that snowballs and feeds on itself. Instead of adding a constant increment at each step as in linear growth, exponential growth involves multiplying by a constant factor. For example, a bacterial population growing on a petri dish doubles every 20 minutes. If there are 1000 bacterial cells initially, after 20 minutes there will be 2000 cells. After another 20 minutes, 4000 cells, and 20 minutes after that, 8000 cells. Then 16,000, 32,000, and so on. In this example, the exponential function to raise x comes into play. Specifically, if we measure time in units of 2 minutes, the number of bacteria after x unit of time would be 1000 times 2 raised x cells. Similar exponential growth is relevant to all sorts of snowballing processes, from the multiplication of real viruses to the viral spread of information in the social network. Exponential growth is also relevant to the growth of money. Imagine a lump sum of $100 sitting in a bank account that earns a constant annual interest rate of 1%. After 1 year, the sum would grow to $101. After 2 years, it would be $100 times 1.01, which equals 102.101. After X years, the amount of money in the bank account would be 100 times 1.1 raised x. In exponential functions like 2 raised x and 1.1 raised x, the numbers 2 and 1.1 are called the function base. The most commonly used base in pre-calculus mathematics is 10. There is no mathematical reason for preferring 10 over any other base. It's a traditional favorite because of accident of biological evolution, we happen to 10 fingers. Accordingly, we have based our system of arithmetic, the decimal system, on power of 10. For the same reason, the exponential function that all budding scientists encounter first, usually in high school, is 10 raised x. Here, the number x is called the exponent. When x is 1, 2, 3, or any positive whole number, the value of x indicates how many factors of 10 are being multiplied together in 10. But when x is 0, negative, or between two whole numbers, the meaning of 10 raised x is a bit subtracted, as we're about to see. Power of 10. There are many situations in science where we use powers to 10 of each calculation. In particular, when numbers are either very big or very small, rewriting them in scientific notation is a good idea. Scientific notation uses powers of 10 to express numbers as compactly possible. Take the number 21 trillion, much talked about these days in connection with the US national debt. 21 trillion can be written either in decimal notation as, or more compactly in scientific notation as. If for some reason we need to multiply that big number by, say, 1 billion, it's easier to write 2.1 equal times 10 raised 13 times 10 raised 9 equals 2.1 times 10 raised to 22 than it is to keep track of all those zeros in decimal notation. The first three powers of 10 are numbers we run into every day. Notice the trend. The left column x grow additively, whereas the right column 10 raised x grow multiplicatively, as we expect for exponential growth. Thus, in the left column, each upward step adds 1 to preceding number, while in the right column it multiplies the preceding number by 10. This intriguing correspondence between addition and multiplication is hallmark of exponential functions in general and functions of 10 in particular. Because of this response between the two columns, if we add two numbers in the left column, that operation corresponds to multiply their partners in the right column. For example, 1 plus 2 equals 3 on the left translates into 10 times 100 equals 30 equals 1000 on the right. The translation of addition to multiplication makes sense because 10 raised 1 plus 2 equals 10 raised 3 equals 10 raised 1 times 10 raised 2. Thus, when we multiply power of 10, the exponents add, as 1 and 2 do here. The general rule is 10 raised a times 10 raised b equals 10 raised a plus b. A related trend is a subtraction in the left column corresponds to division in the right column. 3 minus 1 equals 1. 3 minus 2 equals 1. 2. 1000 over 100 equals 10. These nifty patterns suggest how to continue the two columns downward towards smaller and smaller numbers. The principle is whenever we subtract by 1 in the left column, we should divide by 10 in the right column. Now look at the top row again. Since subtracting 1 on the left amount to dividing by 10 on the right, the correspondence continues with the new top row that has 1 minus 1 equals 0 on the left and 10 over 10 equals 1 on the right. This reasoning explains why 10 over 0, 10 to the raise 0 is defined as 1 and has to be defined that way and has to be defined that way, a definition that people find puzzling. Any other choice would break the pattern. It's the only definition that continues the trends established farther down in the two columns. Going in this way, we can extrapolate the correspondence is further now to the negative numbers in the left column. The corresponding numbers on the right then become fractions equivalent to power of 1 over 10. Notice that the numbers in the right column always remain positive. Each when the number even when the numbers in the left column become 0 or negative. A potential cognitive pitfall when using powers of 10 is that they can make vastly different numbers seem more similar than they really want. To avoid this trap, it's good to pretend that different powers of 10 form conceptually distinct categories. Sometimes human language do this on their own by assigning distinct names to different powers of 10, as if they were unrelated species. In English, we refer to 10, 100, and 1000 with three unrelated words: 10, 100, and 1000. That's good. It conveys the idea that these numbers are qualitatively different, even though they are neighboring powers of 10. Anyone who appreciates the difference between the 5-figure and 6-figure salary knows that one extra zero can matter a great deal. When the words for powers of 10 sound too much alike, we are led astray. During the 2016 US presidential campaign, Senator Bernie Sanders frequently railed against the exorbitant tax breaks going to millionaires and billionaires. Whether you agreed with him or not about the politics, he unfortunately made it sound like, in terms of wealth, billionaires and billionaires were comparable. In fact, billionaires are much richer than the millionaires. To grasp how different a million is for a million is from a billion, think about it like this: a million seconds is little under 2 weeks. A billion seconds is about 32 years. The first is the length of a vacation. The second is a significant fraction of a lifetime. The lesson here is that we need to use powers of 10 with care. There are dangerously strong compressors capable of shrinking enormous numbers down to sizes we can fathom more easily. That's also why they're so popular with scientists. In contexts in which some quantity varies over many orders of magnitude, power of 10 are often used to define an appropriate measurement scale. Examples include the pH scale of acidity and basicity, the Richter scale of earthquake magnitudes, and the decibel measure the loudness. For instance, if the pH of a solution changes from 7 neutral like pure water to 2 acidic like lemon juice, the concentration of hydrogen ions increases by 5 orders of magnitude, meaning a factor of 10 raised to 5 or 100,000. The drop in pH from 7 to 2 makes it seem like just 580 pt steps, not much of change at all, even though it's really a 100,000-fold change in hydrogen ion concentration. Logarithms. In the examples we've considered so far, the number in the right column, like 10, like 100, and 1000, have always been round numbers. Since powers of 10 are so convenient, it would be wonderful if we could express non-round numbers in the same manner. Take 90. For instance, given that 90 is a little less than 100 and 100 equals 10 raised to 2, it seems like 9 should equal it seems like 90 should equal 10 raised to some number slightly less than 2. But raised to what number exactly? Logarithms were invented to answer such questions. On a calculator, if you type in 90 and then press the log button, you get that's the number. In this way, logarithms enable us to write any positive number as a power of 10. Doing that makes many calculations easier and also reveals surprising connections between numbers. Look what happens if we multiply 90 with a factor of 10 or 100 and then take its log again. Observe two striking things here. 1. The logs here have the same decimal part. Multiplying the original number 90 by 10 increase its log by 1. Multiplying it by 100 increase its log by 2, etc. We can explain both of these facts by appealing to a rule of logs. The log of a product is the sum of the logs here, and so on. This explains why the log of 90 and 900 and 9000 all have the same decimal part. The decimal part is the log of 9, and the 9 is a factor that appears in all of the numbers we've been discussing. The different powers of 10 shows up as the different whole number parts in the logs. In this case, 1, 2, or 3 in front of decimal part. Because of this, if we are interested in the logs of other numbers, we need only work out the logs of numbers from 1 to 10. That takes care of the decimal parts. The log of every other or positive number can then be expressed in terms of those logs alone. Power of 10 have their own job. They account for the whole number part. The general rule in the symbolic form is log A times B equals log A plus log B. In other words, when we multiply two numbers together and then take their log, the result is the sum, not a product of their individual logs. In that sense, logarithms replace multiplication problems with addition problems, which are much easier. This is why logarithms were invented. They sped up calculations tremendously. Instead of having to deal with Herculean multiplication problems, square roots, cube roots, and the like, such calculations could be turned into addition problems and then solved with the help of a lookup table known as a table of logarithms. The idea of logarithms was in the air in the early 17th century, but much of the credit of popularizing them goes to the Scottish mathematician John Napier, who published his description of the wonderful rule of logarithms in 1615. A decade later, Johannes Kepler enthusiastically used the new calculation tool when he was compiling astronomical tables about the positions of the planets or other heavenly bodies. Logarithms were the supercomputers of their era. Many people find logarithms confusing, but they make a lot of sense if you think about them by analogy with carpentry. Logarithms and other functions are like tools. Different tools have different purposes. Hammers are for pounding nails into wood, drills are for drilling holes, saws are for cutting. Likewise, exponential functions are for modeling growth that fits on itself, and power functions are for modeling less violent forms of growth. Logarithms are useful for the same reason that staple removers are useful. They undo the actions. They undo the action of another tool. Specifically, logarithms use the actions. Specifically, logarithms undo the actions of exponential functions and vice versa. Consider the exponential function of 10 to the x, 10 raised x, and apply it to a number, say 3. The result is 1000. To undo that action, press the log x button. Applying it to 1000, returns to the number we started with, 3. The base 10 logarithm function log x undoes the action of 10 to raise x function. They are inverse functions in this sense. Aside from their role as inverse functions, logarithms also describe any natural phenomena. For example, our perception of pitch is approximately logarithmic. When a musical pitch goes up by successive octaves for one to the next, that increase corresponds to successive doublings of the frequency of the associated sound waves. Yet, although the wave oscillate twice as fast for every octave's increase, we hear the doublings, which are multiplicative change in frequency, a sequel of what steps in pitch, mean equal additive steps. Is freaky. Our minds fool us into believing that 1 is as far as from 2, as 2 is from 4, and 4 is from 8, and so on. We somehow sense frequency logarithmically. The natural logarithm and its exponential function are useful as base 10 was in its heyday. It is rarely deployed in modern calculus. It has been superseded by another base that looks abstruse but turns out to be far more natural than 10. This natural base is called E. It's a number close to 2.718. I'll explain where it comes from in a minute. But its numerical value is beside the point. The important point about E is that an exponential function with this base growth at a rate precisely equal to the function itself. Let me say that again. The growth of e to the x is e to the x itself. This marvelous property simplifies all calculations about exponential functions when they are expressed in base e. No other base enjoys this simplicity. Whether we're working with derivatives, integrals, differential equations, or any of the other tools of calculus, exponential functions expressed in base e are always the cleanest, more elegant, and most beautiful. Aside from its simplifying role in calculus, base e arises naturally in finance and banking. The following example will reveal where the number e comes from, how it defined. Imagine you deposit $100 in a bank that pays interest at an implausible but irresistible annual rate of 1%. That means that after 1 year, your $10 become your $100 become $200. Now start over and consider an even more favorable scenario. Imagine that you could persuade the bank to compound your money twice a year so that you could gain interest on the interest as your money goes. How much more would you earn in that case? Since you are asking the bank to compound the money twice as often, it's only fair that the interest rate for each 6-month period should be half as large, namely 50%. Thus, after 6 months, you'd have 100 times 1.5 which equals 150. 6 months later, at year's end, the amount would be another 50% more. 150, 150 times 1.50, which equals 200 to 225. That's more than $200 you got under the original arrangement, because you gain interest on the interest during the year. The next question is, what happens if you could get the bank to compound your money more and more frequently at correspondingly smaller interest rates during each compounding period? Will you achieve fabulous wealth? Unfortunately, no. Compounding quarterly will yield 100 times 1.25 power 4 approach $244.14. Not much of an improvement over 225. Compounding still more rapidly once they for the 365 days in the year would leave you with only at the end of the year. Here, the 3065 in the in both the denominator and the exponent refers to the numerator of compounding periods in the year, and 1 in the numerator of 1 over 365 is the 100% interest rate expressed as a decimal. Finally, suppose we take this compounding madness to the limit. If the bank compounds your money n times a year, where n is a monstrously huge number with correspondingly tiny interest rates during each sub-nanosecond period, this by analogy with the result for 365 daily periods, you'd have in your account at year's end. As n approaches infinity, this amount approaches 100 times the limit of as n approaches infinity. This limit is defined as the number e. It's not at all obvious what the limiting number is, but it turns out to be approximately 2.71828. In the banking world, the financial arrangement above is called continuous compounding. Our results show that it is nothing to get excited about. In the problem above, it will yield a year-end balance of $100 times E equals 271.83 dollars. That's the best deal. That's the best deal yet. But it's only 37 cents more than the result of daily compounding. We just jumped through a lot of hoops to define E. In the end, he turned out to be a complicated limit. It has infinitely built into it in much the same way the number pi does for cycles. Recall that pi involved a calculation of the perimeter of many-sided polygon inscribed in a cycle. The polygon approaches the cycle as the number of sides n approaches infinity and the length of those sides approaches 0. The number e is defined in a somewhat similar way as a limit, except that it arises in the different context of continuously compounded growth. The exponential function associated with e is written as e power x e raised x, just as the exponential function for base 10 is written as 10 raised x. It looks weird at first, but at the structural level it's just like base 10. All the principles and patterns are the same. For example, if we want to find an x such that e to the x e raised x is a given number, say 90, we can again use logarithms as we did before, except now we rule out the base e logarithm, the base known as the natural logarithm and denoted ln x. To define the unknown x such that e power x equals 90, turn on a scientific calculator in enter 90. Press the ln x button and there's your answer. To check it, keep that number on the screen and hit the erase x button. You should get 90. As before, logs and exponentials undo each other's action. Less stapler and a stapler remover. Recondite as all this may sound, the natural logarithm is extremely practical, though often inconspicuously. One thing, it underlies a rule of thumb nouns to infer stocks and bankers as the rule of 72 to estimate how long it will take to double your money at a given annual rate of return. Divide 72 by the rate of return. Thus, money going at a 6% annual rate doubles after about 72 over 6 equals to 12 years. This rule of thumb follows from the properties of the natural logarithm and exponential growth and works well if the interest rate is low enough. Natural logarithms also operate behind the scenes in the carbon dating of ancient trees and bonds in authentication disputes. A famous case involved paintings alleged by Vermeer that turned out to be forgeries. This was revealed by analysis of the radioactively decaying isotopes of lead and radium in the paint. As this example suggests, the natural logarithm now prefers all fields where exponential growth and decay arise. The mechanism behind exponential growth and decay. To reiterate the main point, the thing that makes E special is that the rate of change of e raised x is e raised x. Hence, as the graph of this exponential function soars higher and higher, its slope always tilts to match its current height. The higher it gets, the steeper it climbs. In the jargon of calculus, e raised x is its own derivative. No other function can say that. It's the fairest of them all, at least as far as calculus is concerned. Although base e is uniquely distinguished, as other exponential functions obey a similar principle of growth. The only difference is that the rate of exponential growth is proportional to the function's current level, not strictly equal to it. Still, the proportionality is sufficient to generate the explosiveness we associate with exponential growth. The explanation of the proportionality should be intuitively clear. In bacterial growth, for example, bigger populations grow faster because the more cells there are, the more of them are there available to divide and make offspring. The same is true with the growth of money in account being compounded at a constant interest rate. More money means more interest on that money and hence a faster rate of growth of the overall account. This effect also accounts for the whole of a microphone when it picks up the sound of its own loudspeaker. The loudspeaker contains an amplifier that makes a sound louder. In effect, it multiplies the volume of the sound by a constant factor. If that louder sound gets If the louder sound gets picked up by the microphone and then sent back to the amplifier again, its volume will be amplified repeatedly in a positive feedback loop. This causes a sudden exponential runaway of volume, going at a rate proportional to the current volume and leading to the awful screeching sound. Nuclear chain reactions are governed by exponential growth for the same reason. When a uranium atom splits, it fires out neutrons that can potentially smash into other atoms and cause them to split, sending out still more neutrons, and so on. The exponential growth of the number of neutrons, if left unchecked, can set off a nuclear explosion. Along with growth, decay can be described by exponential functions. Exponential decay occurs when something is being depleted or consumed at the rate proportional to its current level. For example, half the atoms in an isolated lump of uranium always take the same amount of time to decay radioactively, no matter how many atoms were present in the lump initially. The decay time is known as the half-life. The concept applies to other fields as well. In Chapter 8, we'll discuss what doctors learned about AIDS after they discovered that the number of virus particles in the bloodstreams of HIV-infected patients dropped exponentially with a half-life of only 2 days. After a miracle drug called a protease inhibitor was administered. These differs examples from the dynamic of chain reactions and microphone feedback how to the accumulation of money in a bank account make it seem like both exponential functions and their logarithms are firmly planted in the part of calculus that deals with changes in time. And it's true that exponential growth and decay are prominent topics on the modern side of the crossroads of calculus. But logarithms were first cited on the other side, back when calculus was still focused on the geometry of curves. Indeed, the natural logarithm arose early on in studies of the area under the hyperbola y equal 1 over x. The plot thickened in the 1640s when it discovered that the area under the hyperbola defined a function that behaved uncannily like a logarithm. In fact, it was a logarithm. It obeyed the same structural rules and turned problems of the multiplication into problem of addition, just like any logarithm. But its base was unknown. There will still much to be learned about the areas under curves. It was to be one of the two great challenges ahead for calculus. The other was to devise a more systematic method to find the tangent lines and slopes of curves. The solution of these two problems and the discovery of the surprising connection between them would soon take calculus and the world decisively into modernity.